So I want to talk today quickly about an ongoing project that we're working on about securing the cloud, aka other people's computers, and partially just to inform you, and partially also as sort of a call for help. If some of the things I'm discussing appeal to you, feel free to come and talk with me afterward or send me an email. So there's this thing called the cloud. So other people's computers, this is useful when we want to interact with big data. Because if we have a lot of data, we don't necessarily want to store it ourselves. And partially because it's annoying, it's big, and partially because then it's hard to share with other people. If we already store it outsourced to someone else's machine, then it's easy to give data to somebody else. It's just an access control problem rather than a networking problem. And also, with the large amount of computing power that comes on these other people's machines, we can also use those resources to be able to have every individual or organization that has access to this data can analyze this to produce some sort of something that's more meaningful to them. So cloud computing is a cool thing, but unfortunately it's not actually something, this cloud in the sky. There's underneath it, there's actual machines and like decades of research and innovation into software and hardware and networking into making all of this stuff work, all these crazy stacks of stuff. So what we're interested in is how do you secure this large behemoth of infrastructure? So what we're good at doing today is providing individual system security protections against individual components of the cloud to protect it against specific types of threats. So for instance, we can protect our hardware against some sort of tampering or side channel attacks. We can ensure that our networking is not vulnerable to eavesdropping or spoofing. We can isolate an operating system from vulnerabilities in user space software. We can encrypt data at rest. We can even do so in a database in a smart way so that it can still be searchable. So we can do all of these individual protections at different levels. And the question that we have is that sufficient? Does that suffice to produce an overall cloud environment that is secure for a given application? But unfortunately, this is not always the case. Composition is a very finicky problem in security, and if you're not careful, the answer to this question of composition is usually no. So that's where we come in. What we want to do is replicate sort of what the software engineers and hardware engineers have figured out over the last 3 decades to do in even constructing a cloud in the first place. An environment so complicated that no single human can explain all of it, and yet we can still build it and it still works. And the key notion that enabled this is modularity. So each of the components of the cloud is designed in such a way to abstract as much as possible from what the other components are doing, other than some sort of thin shim that we can call an API. And as long as all of these individual components obey this API, and as long as they provide all of the conditions that other components are expecting, all of these nicely combine to form a nice cloud, and in this nice way of puzzle pieces combining using the magic of PowerPoint. And then the nice thing about this combination piece is that all we have to do to make sure that from a correctness and functionality standpoint that these pieces combine is understand that we've produced the right API. It doesn't even matter how each of these components were instantiated under the hood. So what we want to do is something similar to this for security. So as far as I can tell, you need 2 things to make this work. One is a bunch of people who know everything about all the security and security of all these different components, software and hardware and networking and applications and databases and so on. So you need a bunch of people. So okay, we have people that know stuff about cloud security. And the second thing is you need to figure out the question about how the puzzle pieces fit together. And so that's the key technical challenge that we're trying to deal with. And to address this, we are looking at the universal composability framework. If you're not familiar with this framework, I can't really do it justice in a short talk. But the basic idea, the key innovation, is that it provides one nice clean mechanism to separate the problem of what security guarantees you're claiming something provides from how you go about proving that it attains such security guarantees. So you, whatever piece of hardware, software, whatever you're concerned about, you imagine you live instead in some sort of ideal world in which there was some magical entity that everybody trusted, and you figure out what is the kind of functionality that you would want this trusted box to perform, what is exactly the amount of information that would be transmitted to all parties in your ideal world, and then separately from figuring out what that thing is, you then have to figure out a way to argue or prove that your real-world instantiation is actually a faithful real-world implementation of this ideal vision that without having this trusted box around it somehow computes and reveals no more information than that trusted box does. So I want to argue in the time remaining that this UC model is very useful, even for problems outside of the traditional cryptographic algorithmic view. So I'm going to focus on how this nice simple abstraction, which leads to a nice composition theorem, that this can be useful for things other than cryptography. So I'll give you two examples. The first one is computing on big data obliviously, which is a topic that was discussed at length yesterday, so I won't belabor it. We have some small client that wants to outsource a computation to a larger cloud server. Let's suppose that the client trusts the server from the standpoint of correctness, integrity of the result, but just wants to make sure that the server computes the answer without learning anything about the client-sensitive data. So we've seen three very different solutions to this problem. One that Elaine discussed this morning involves secure hardware. So if you have something like Intel's software guard extensions, you can have your computations be performed over data that is encrypted when it's in memory, but then it gets sent to a processor. It gets decrypted only at the processor. The computation is performed, and the result is re-encrypted before being sent out to untrusted spaces. So if this trusted hardware mechanism correctly keeps your keys secret, and it keeps its keys secret, and performs and isolates your computation from that of everybody else on the machine, then the system works even if you don't have any trust in anything other than the hardware. A very different solution to this problem is homomorphic encryption, which Vinod discussed yesterday morning. This is a very clean, beautiful algorithmic primitive that works very nicely. From a trust standpoint, the main things you have to be concerned about are making sure that the software that actually implements the FHE is a faithful instantiation of the algorithm you wanted, and also that something on your machine, like say your operating system, is protecting your keys from exfiltration. A third solution to this, which addresses sort of this key exfiltration problem, is to use secure multi-party computation to split or secret share your cryptographic key material amongst multiple different machines, and have some way then to trust that there is some upper bound or threshold as to the fraction of nodes that are compromised. Perhaps this could be instantiated through some sort of network isolation or heterogeneity guarantees. So these are three very different solutions to the problem that involve different layers of this cloud infrastructure. But what we can do with the UC model is model them all as three instantiations or solutions to the exact same problem, that they have the same ideal objective, which of oblivious computation. So the UC model gives us this language to model this common problem and the framework to argue individually about the oblivious guarantees of each piece. And then a user on the cloud who wants this thing called oblivious computation knows that all of these three different solutions actually do solve the problem that she's concerned with, and then only has to make a decision as to which solution to use based on which set of trust guarantees, trust assumptions she's willing to make, and how much cost and what the performance is of each solution. A second example I want to give is to show how this UC framework can be helpful in analyzing software. And to do so, I'm going to discuss OpenStack, which is an open source cloud computing platform. It's basically the open source version of at least a subset of what Will just discussed for AWS. I'll try very briefly to describe how OpenStack works in 1 minute, which is kind of tough because it's almost 2 million lines of code, but I'll give it a shot. So, okay, OpenStack. There's a cloud and there's users. It's pretty simple. Okay, maybe it's not that simple. I'll peer down a little bit. So what we want to do is give people the ability to do stuff on other people's machines. And so I'll illustrate how these different components of OpenStack work by example. So suppose I want to have a virtual machine on the cloud that has the Ubuntu 15.10 operating system running and gives me some amount of computing power, say the equivalent of my machine right here, and 100 gigabytes of storage space. So OpenStack is split into these different services that do these different operations. So first I would talk with this service called Keystone, which authenticates who I am and checks that I'm authorized to perform the operation that I want, in this case create a new virtual machine. Then I would talk to a service called Nova that actually has these banks of computing power. I would also talk with this service called Glance, which has images. So if I want an Ubuntu 15.10 image, it would be rather inefficient if every single user uploaded a virtual machine image to the cloud. Instead, it has a bank of them available for use. And then there's a service called Cinder, which has arrays of hard drives available. So So I would get some computing power from Nova, and that would get attached to some block storage, some storage at Cinder, and the image from Glance would instantiate my virtual machine. And this is as well an abstraction. You know, all of these have lower level, all of these services have a bunch of machines working under the hood. So for instance, the Nova service has, you know, a bunch of worker nodes that are able to provide computing power to anybody who wants it, and some sort of intelligent scheduling mechanism that dictates, you know, which machine is the most free and available for use. And there can be multiple different OpenStack deployments in the same cloud as well. So this is kind of neat that we have these security concerns at 4 very different levels of the cloud. There's the user versus cloud dilemma that the cryptographers are typically concerned about. There's even security within the cloud between different OpenStack deployments between different services of a single deployment, and even within a single service. And here's where the magic of universal composability can help us. So rather than looking at like a 1.75 million lines of code of OpenStack, we can try to break it up and think about what each individual endpoint or each individual service is supposed to provide, and provide an idealized version of what each of these things is supposed to accomplish. And now we're looking at small enough manageable pieces of code that we can actually try to analyze and argue somehow that the real code meets this ideal view. So we can argue that all the different endpoints of Nova, their ideal versions can compose to form an ideal Nova service, and so on. The secure services compose to provide a deployment, and so on. So in summary, we're trying to UCify all the mechanisms for cloud security. The goal is to get a cloud with some nice, meaningful, and modular security guarantees that are readily understandable to users and enable users to make informed decisions about sort of security, performance, and trust trade-offs. If you're interested, please feel free to contact me via email. Thanks.